Hello and welcome back to Calculus. First, I want to thank all the nice people that support this channel by liking and subscribing. Today, in part 35, as promised, we will take a trip down memory lane and revise limits. More specifically, a method to evaluate limits under a certain condition. Now, please recall from part 2, a limit, denoted by lim, tells us the value of a function as x approaches a certain value. Hence, we write the limit as x approaches something, let's just say it's a, of another function f of x. And the answer when you evaluate that you get should be a real number. Now, x can approach anything. It can approach 0, it can approach negative values, it can even approach infinity. However, many limits are impossible to evaluate using analytical method that we did in part 2. Thus, a new rule called the L'Hopital's rule exists. However, the condition that must be met before applying L'Hopital's rule is that when evaluating the limit directly, the answer we get is indeterminate. Indeterminate just means we get 0 divided by 0, or we could also get infinity divided by infinity. These two cases are indeterminate, and only if these two conditions, or one of them, is gotten when we evaluate the limit directly, only then can we apply the L'Hopital's rule. For this, I want you to consider an example. Let's say we're tasked with evaluating the limit as x approaches 0 of the function sine x divided by x. A direct valuation of this limit, meaning plugging in 0 for x, leads to ambiguity, because sine of 0 is 0, and on the bottom we just have 0. We get 0 divided by 0, which is indeterminate, or otherwise also known as undefined. This is because both functions in the numerator and in the denominator approach 0. Thus, their ratio is undefined. However, since we know derivatives, and we also know that derivatives represent the rate of change of a function, what if we do the derivatives of the upper function sine and the lower function x separately? Well, the derivative of sine is the cosine function, and the derivative of x is simply 1. So now my limit as x approaches 0 becomes cosine of x divided by 1. This means that we are now evaluating the ratio of their rates of change rather than the functions directly. So now let's evaluate this again directly. In the numerator, cosine of 0 is 1, and on the bottom it is just 1. So now the limit is successfully evaluated, which is equal to 1. And this showcases the L'Hopital's rule. It states that if we are evaluating the limit as x approaches a certain value a of a rational function in the form of one function divided by another function, in our case f of x over g of x, and when we try to evaluate the limit directly, meaning by plugging in a, so f of a divided by g of a, and the answer we get is either 0 over 0 or plus minus infinity divided by plus minus infinity, then we can evaluate the derivatives of the upper and lower functions separately. And then just take the limit as x approaches a from that. And we should arrive at a real number, or at least not indeterminate or undefined. However, there are cases when we need to apply L'Hopital's rule more than one time. I want you to consider the limit as x approaches infinity of the function x squared minus 1 over x squared plus 1. When you evaluate this directly, what we get is infinity minus 1 and infinity plus 1. So technically just infinity over infinity, which is undefined. So now let's do the derivative of the function in the numerator. What we get is just 2x. Derivative of the function in the denominator is also just 2x. However, here comes the problem. Even after doing L'Hopital's once, when we try to evaluate this directly, once again we get infinity over infinity. So now that means we can apply L'Hopital's again and do the derivative of the upper and lower functions separately. In the numerator, we just have 2 left, and in the denominator, also just 2. And this time, when we try to evaluate this directly, well, there's nothing to evaluate technically because there are no more x variable left. What we get is 2 divided by 2, or just 1. And that is it. Very simple and very straightforward. So I think that's enough for today. In the next video, we're going to start something new and mainly see what calculus and polynomials have in common. So I hope to see you there and have a nice day. Bye.